discussing a paper by Richard Sutton about plasticity of learning. It's something that he published last, I think, summer or fall in 2024. And we already discussed an interview that he gave of How I Really Feel, which was sort of subsequent, let's call it a little bit of a marketing tour that he did for the paper. So we want to revisit this paper because he also gave a speech recently at a conference about this particular paper and about the plasticity of learning. Now, the idea of plasticity of learning in general is the ability of a model to keep learning with new data and getting better at solving problems, whether it's existing problems that has already learned, and also acquiring the ability to learn and get better at new types of problems. So in concrete terms, that means that hopefully at some point we can get to like a Tesla FSD model, for example, that continuously learns with new data and appreciates the ability to solve new problems with new data. That is not the case right now. The way AI works right now, the state of the art is that we train a model and then we deploy the model, and then we train a new model and we deploy the model. So we're not able to actually use an existing model and add new data to the model and get better at it. Now, there might be other endeavors that I'm not aware of. Please put it in the comments if other models, maybe Google, maybe Grok, maybe Tesla, maybe others have been able to actually solve this problem. But the plasticity of learning it means that we want to maintain the knowledge of a model but keep adding to the ability of the model to solve problems with new data. And that's different from catastrophic forgetting or the avoidance of catastrophic forgetting, which is where we actually erase knowledge that has been acquired and learn new things but forget new things. So that's a little bit different. But in essence, what Sutton is talking about here is, in particular, the ability to continuously learn. So you don't have to have these huge batches of learning which require millions and millions of dollars. You could potentially just keep adding to an existing model, and that's currently not in the cards. Like currently, that's not how models are trained. We see that by just the announcements of X or OpenAI. It takes them months to release a new model. That means they have to train a new model, and that is, in my opinion, it's very expensive. It's also kind of cumbersome, right? And you could have much faster, much more efficient learning if you had continuous learning. So how do they solve this problem? There's two techniques that they use. One is L2 normalization, which has been around, and then continual back-propagation, which is the innovation that Sutton et al. Bring to this paper. This is the Not Even Wrong podcast. It's August 17, 2025. This is Krim Delco. For the year, we are down 9.3%. The market is up 9%. We're underperforming by 18.3%. This paper, links in the show notes, interviews in the show notes. We also have a link to a former discussion that we had here at Orange Capital Partners, and also a former video. So there's a bunch of events that have already happened related to this concept of plasticity of learning. I think what we want to focus on here is really two things. One is the techniques, and the other is what this could imply, the implications for AI going forward. So let's set the stage first. I mean, Richard Sutton wrote The Bitter Lesson. I think the bitter lesson is a fundamental concept, a fundamental philosophy for AI going forward. I think it's going to shape the development of AI for the next decades. So therefore, it's I think it's something akin to the categorical imperative by Immanuel Kant. Like in 200 years, people will talk about Sutton as sort of the Kant of AI, or the philosopher, scientist, researcher who really put AI on the stage as it's supposed to be brought on the stage. And of course, his disciple, David Silver, who created AlphaGo Zero, who, in my opinion, really showed the world what AI can do in terms of real intelligence, not just some game intelligence like classifying images and stuff. So back to, so what's the bitter lesson mean? The bitter lesson means more data, more to compute, better intelligence. The question now is, of course, how do we do this, right? Do we do these huge batches every 6 months, invest billions of dollars into training a whole new model, or can we have continuous learning? That would be ideal, right? We just keep adding new data onto the model and it keeps getting better. Well, it doesn't work like that. And the technical reason for why it doesn't work like that is that, let's call it like neurons get saturated. So the incoming weights and the outgoing weights kind of start, they become rigid. There's not, there is a lot of learning that happens in the beginning. Think of it like a child that learns very early on and is very has a lot of plasticity, learns. But then, when we become adults, we just stop learning. We become stubborn. It's hard to teach new tricks to an old dog kind of thing. So we humans have that same, we show that same, characteristic. And the way we fight this as humans is we change our lives. We travel. I mean, this is, Thomas Mann in Zauberberg writes about this. There's a passage where he writes about this. Let me quote this passage, actually. It's a beautiful passage. So just give me 1 second. I'm going to get the passage. Wir wissen wohl, dass die Einschaltung von und Neugewöhnungen das einzige Mittel ist, unser Leben zu halten, unseren Zeitsinn aufzufrischen, eine Verjüngung, Verstärkung, Verlangsamung unseres Zeiterlebnisses und damit die Erneuerung unseres Lebensgefühls überhaupt zu erzielen. Dies ist der Zweck des Orts- und Luftwechsels, der Badereise, die Erholsamkeit, der Abwechslung und der Episode. Now, this is Mann talking in the Zauberberg, beautiful little quote. But I think what he means with that is that, we got to shake things up. We got to change. We got to put ourselves in uncomfortable situations. We got to put ourselves in new situations because we want to rewire our brain. And that's exactly what Sutton is talking about now. He's defining intelligence, which is very interesting, actually. His definition of intelligence is a model that can determine its own data input and rewards. So it finds out what it needs to get better and also what kind of rewards it needs to achieve its goals. Just as a side note, he's not talking about defining its own goals. So that is something that I guess stays in the realm of humans. But finding ways to achieve those goals, that should be left alone to the AI, and that's, I think, the fundamental thesis of the bitter lesson. Don't put any human judgment in the way. Now, back to the actual techniques. So the two techniques, L2 normalization and continual back-propagation. L2 normalization means that take a vector, any kind of length vector, and normalize it by its length. So always keep it between 0 and 1. That means that you have large weights cannot overwhelm the network. And on the other hand, the continual backpropagation changes outgoing weights of neurons. So randomly changes outgoing weights of neurons that have little or no impact on the results of the learning. What does that mean? So let's say we train a model. Let's say in the case of this paper, the Nature paper, they used actually ImageNet as a test case. And there, let's say you start with tasks, you train the model to distinguish between dogs and cats, and it gets really good at that. But then you keep adding new tasks, for example, distinguishing between trucks and cars. And the particular neuron that is really good at pointing out pointy ears and therefore finding the difference between cats and dogs starts losing its value when it comes to trucks and cars. So what we do there now, we reinitialize the outgoing weight. We keep the ingoing weight. So if there's another dog showing up, it will be able to distinguish between a dog and something else. But it doesn't help in other features, for example, trucks and cars or trees and flowers. Now the hope is that this particular feature that is good at pointy ears can be kind of plasticity, can have plasticity. It can be retrained. The ingoing weight doesn't change, but the outgoing weight changes. So the ReLU function, in the end, the nonlinear activation function, actually gets activated for something else, maybe color or maybe tree versus flower or something like that. So that's the fundamental idea. Sutton himself agrees that we actually don't know quite now why this is happening and how to improve it. It's a new area of research. It's one of those things where, you know, he says, look, we should be focusing on what we can't do and not only what we can do, and that's fine. I think as scientists, that's what they should be. I think that's, in my opinion, that's the definition of a scientist. You start thinking about things that you can't do, versus the engineer and entrepreneur focuses on what you can do and goes from 0 to 1 and then scales and all that. So to summarize, I think continual back propagation is a really interesting idea for a technical explanation for the actual problem of increasing plasticity in a model. L2 normalization also. Fundamentally, back propagation in its form, the way it's designed, is meant for transient learning. So you kind of have this model, you do back propagation and you get to an optimal point and that's it, you can't get better. If you add new data, it doesn't get better, so you have to retrain the model with new data and larger scale and get better results. That's where we stand today. It's expensive and it's slow. If we could have continual learning, that would, you know, increase the iterative abilities of our models. It would increase the speed of adaptation of intelligence and make everything much better. But we're not there yet, and that's what Richard Sutton is working on. I think as far as Tesla is concerned, which is very interesting, of course, that would be amazing for robotics. I think this is the holy grail of robotics, and Sutton even doesn't talk too much about it, but he's, of course, a reinforcement learning guy, and reinforcement learning is the holy grail of robotics. And if we could have continual learning for robots, that would be, I think, that would definitely put us on a stage where we could have kind of Robinson Crusoe type robots that really figure out themselves what they need to do to achieve certain goals. As far as FSD is concerned, we could have continuous learning. Imagine a fleet of millions of cars driving millions of miles per day and continuously getting better at solving the driving task. So as usual, Richard Sutton, very inspiring, very interesting, and very important. Thank you.